Okay, welcome. This is the week 5 webinar. This is the week 5 webinar. And let me tell you the plan, as always. We'll start out. If there's any questions you might have, feel free to ask. And you can pop them in the chat box. You can ask on your microphone. If you put in the chat, it's private. So just let you know. And but again, this is it's a biggie. It's the most important theorem of all statistics, actually, we're talking about. But we'll start out getting ready for that we'll talk about sampling distributions. And basically, statistics really is all about taking samples. And we want to look at a certain distribution based on that. We'll look at biased and unbiased estimators. And then we'll have the big theorem. And I split it into 3 pieces. The central limit theorem for means, the central limit theorem for proportions, and the central limit theorem for sums. So we're going to have 3 big theorems that we're going to be basically referring to for the rest of this course. So this is an important day to be able to handle that. So that is the plan. Are there any questions that you have? Any questions? Okay, feel free throughout the whole webinar. If you have any questions, pop in the chat box. And definitely, I'll always have an eye in the chat box and I'll be able to look at it. I want to show you something that I literally added 3 minutes ago to the course. But it's something I've been working on for a long time. And it's what's new. What do you think is brand new? What new thing do you think I can add to an online class? Any guess? It's like truly new. Like 5 years ago, we wouldn't even like mention the possibility of it. Let's see y'all jumping in. All right, let me go to the syllabus, which I just updated literally a few minutes ago. And I popped it in because I literally got the email about it, that it was ready. Not even 5 minutes before the webinar started. So, and that is embedded artificial intelligence into the textbook. So there is now the ability to go to the textbook, the older version of the textbook. They don't have it in the newer version yet, but the older version of the textbook, but statistics doesn't change. That's the good news. And you can use AI. And what this does is this gives you a link to the user's guide on how to do it. So I'm not going to spend, hours talking about it, but you can kind of see. And what it's called, you probably might have heard of ChatGPT. There is a kind of a cousin of it called Math GPT. And that is artificial intelligence to help you with your math. Okay, it won't help you cheat, by the way. It won't answer, questions that are on the test and stuff like that. But it will help you when you're reading the book get some kind of further information. You ask whatever questions you want, and it'll give you guidance. So again, I'm not going to go through this whole PowerPoint because it's 27 slides and we only have so much time. But let me know. All of your emails are at least put in here. Again, this is the first time ever trying it. I'm actually the pilot for the system, so they don't even know really well. Hopefully it'll work because it's never been used before. But if it does, again, it's brand new. Kind of cool. So that is the new thing in the course. And that is artificial intelligence to answer any questions as you're reading the book. Kind of cool. All right, so now what I want to do is, you may not have quite enough people here to be able to do this example. So I'm going to have to change the example. Let's do another example. What I want you to do is I want you look up five baseball players. Actually, maybe 3. And find the mean, which is the average, and standard deviation of their ages. Very easy, just ask the computer, what is the age of? And then put a baseball player, put another one, put another one. You shouldn't take more than 30 seconds to do that. You got to type, what is the age of? Or how old is probably easier. And if you don't know any baseball players, just go to, I don't know, some baseball website, or just say, give me names of 3 baseball players, and Google or whatever you use will do that. Let's see if you can give me the ages. Put it in the chat box. The ages of 3 baseball players they're currently playing. So, don't give me Babe Ruth, because that was many, 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 many decades ago. Let's see if you can put them in. Maybe I'll do it as we're talking, so you'll know how to. Give me age, 3 professional baseball players. Google's very good about it. Here we go. Rich Hill is 43. Nelson Cruz is 42, and Adam Wainwright was 41. Okay, that's how fast it is. You should be able to do it. I'm not seeing it in your chat box. I'll put mine in. That's how simple it is. A lot easier than it used to be in the old days. Let's see if you can do it. So I have 43, 42, and 41. I just happen to have. And then if I want the mean and standard deviation, very simple. I just go to one variable statistics calculator. And then I know the mean is going to be 42. I can do that in my head, but 43, 42, 41. This is definitely a sample. And I calculate. And the mean was 42. The standard deviation was 1. So you do it also. I need some data, so it's important that you do it. And I'll even, while you're doing it, I'll put it in nicely. Instead of mean, I'm going to write it as it should be, which is X bar. Insert. There it is. See, I'll put in the chat box. I need you to put in the chat box because we need this to be able to really understand what's going on. And the standard deviation is S because it's a sample standard deviation. Let's see what yours are. So again, just get the numbers of 3 and then give me the mean and standard deviation. Shouldn't take more than a minute or two. It's already been 5. Okay, we got 1 age and then 2 more. One more. hoping this would go faster. And then I'll see the rest of the class doing it. And 31 wiki bets. Okay, and then quickly I'll just do it for you then. Copy. Paste it in here. And calculate. 30.7 is the average. Copy and paste. And the standard deviation was 1.5 about. Okay, so what's important here, and this is why I'm kind of gave you at least we have example 2, but I was hoping with more. You'll notice that we have sample sizes of 3. I have an X bar, that was the mean, the sample mean for the first sample. I have a S, which is the sample standard deviation for the first sample. And then we tried another one, 29, 32, 31, and we got an X bar. Notice the X bars are not the same. And that's how it's going to be, right? You take a sample, you get a sample mean, take another one, you get a different sample mean. And same thing with standard deviations. They're not the same either. So one problem is that if you conduct a survey, you take a sample, you're going to get a mean. But then if someone else conducts the same survey with different people, you're going to get a different mean. So the question is, how reliable is this? And we can look, let me just put this in. Google's great. What is the average age? Professional. Baseball players. And the average age? Let's see. 20 to 30. That's not what I was hoping for. Here we go. 29.33. Okay, so that is mu. So our mean, our population mean is 29.33. But the sample means are different. In fact, we both got older than that. Okay. And then we can also look at the standard deviation. What is the standard deviation of the age? Let's see if Google will tell me. I hope so. And standard deviation is, we're just gonna pretend this was right. 4.4 years, even though it's not quite right, but we'll just pretend. Okay, which is very different than what we got. Okay, you're not going to get the same thing in a sample. Okay, but the whole point of taking a sample is to get an idea of what the population is all about. Does that make sense? So that's what sampling is about. And what we want is we want to say, well, how good an estimate is our sample mean? Because the sample mean is an estimate for the population mean. And you'll notice that, we got 2 different sample means. We could do this all day long. We get 100 different sample means and look at them, and you're gonna have a bunch of numbers. And they're gonna be different, pretty much all different. And how different? My guess is you'll never get a sample mean of 100 because that can't happen for baseball players, professional baseball players. But you'll get sample means all over the place. So one of the thoughts is you could take the sample mean And you can look at the distribution of all possible sample means. So for example, you can do a histogram and you can look at it and say, well, does it look, does it look skewed left? Does it look skewed right? Is it approximately normal? Is it bimodal? Kind of what is the distribution? What's the shape? How about if you look at all the different sample means, then you can say, what is the mean of those? All right, we got two of them. We can average those two, but if you average all possible sample means, what would you get? And similarly, you can look at all possible sample means, and you can say, what is the standard deviation of all possible sample means? Any questions on that idea? Because if you have a bunch of numbers, you can find the mean and the standard deviation of those numbers. Okay, that is the sampling distribution. So the sampling distribution is the distribution of all possible sample means. Okay, very important thing. Any questions on that? And pretty much we're going to assume that the sample size are always going to be the same. Okay, so the idea is you can imagine, well, if you take, 1 million different samples of size 3 of ages of professional baseball players, then you can look at the distribution of all those sample means. Any questions on the idea? Okay. So it turns out you want to say, well, what is the population mean of all those sample means? The symbol we're going to use, well, when we talk about population mean, we use mu. When we talk about sample mean, we use x bar. So if you want the population mean of all possible sample means, we write it as mu subscript x bar. And that's the way to do that. But I just want to give you a warning. It is a bit technical to get that typed out like I did. Not impossible, but technical. So, if you want to make it pretty, then you might need some help, especially the first time you do it. Be careful in Canvas of copying and pasting some of these things, because sometimes when you copy and paste, like for a discussion forum, and you hit submit, it dies, and you end up with a nothing. So that's just a heads up warning, is that in Canvas, you got to be very careful. Okay. I know how to do it, but it's technical. You could try, but make sure that anytime you have any kind of symbol that you put in Canvas in your discussion forum, after you hit submit, take a look to make sure it actually shows up. Go back to the discussion board and make sure you can see it. Because I see that's a big problem I see lots of times. People think they type something in, it looks beautiful, they hit submit, and it just cleared everything out. So don't do that. Any questions so far? Okay. Not only can we talk about the mean of all possible sample means, if you have a whole bunch of sample means, that's a whole bunch of numbers. And if you have all those numbers, you can take the mean of them, but you can also take the standard deviation of those numbers. And if you look at all possible sample means, then the standard deviation of all possible sample means, we're going to use sigma, because that's standard deviation of everything, right? That sigma is for the population standard deviation. But it's of sample means, so we do subscript x bar. And again, it's a bit technical to type that out. If you're ever putting it on an exam or on the discussion board, you're welcome to put that in some words if you want. And you can type in SIGMA, and then you can do a little underscore thing, and then XBAR, and that's fine. I'll accept that. Okay, on your project, but it's a little too early to even talk about it, but project 2, you're gonna be doing this, and that I want you to do it in symbols, because that one you can get help on, and you have weeks to do it, that kind of thing. So don't do it at the last minute, by the way. And I guess I should remind you, what's the big thing that's due Sunday? Okay, besides just the assignment for the chapter, discussion thing, but what's the biggie? Yeah, project one. So make sure you get that project one in on time. It's and I really want you to send me, if you haven't already, to send me your rough draft. And it should be hopefully sent maybe this afternoon today, maybe tomorrow. The absolute last chance will be 8 a.m. on Thursday, but if everyone sends it on Thursday morning, early morning, then I may not have time to read them all. It might be hundreds of pages. So that's one thing, and I read them on the first submitted, first read basis. So if you're last minute, then I may not even get to yours until Sunday, and then that doesn't give me enough time. So that's just a note, is don't wait till the last minute to submit your rough draft. Okay. And I only read one draft, but after reading the draft, I'll give you lots of suggestions. If there's a suggestion you don't understand, just post on the discussion board, the project discussion board, about not understanding something. Don't submit your whole draft again on the discussion board, but just write a sentence or two on what you don't understand. You can also get help from the tutors. So make sure you do get the help you need. So I figured I should mention the projects. Okay. And by the way, people have asked, you must have at least one partner. You're allowed to have up to 3 people in the group. One, in other words, by yourself is not okay. So that's a big thing. All right, so let me mention again, the mean of all sample means is notated by mu sub x bar. The standard deviation of all possible sample means is noted by sigma sub x bar. A lot of people will call this sigma sub x bar, because it's a lot of words to say the standard deviation of all possible sample means. They just call it the standard error. So that's the word we use to talk about the standard deviation of all possible sample means, is just standard error. Any questions? Okay, we've already defined the sampling distribution. Let me talk about estimators. So a statistic is called an unbiased estimator for a parameter. Remember, a statistic comes from the sample. Parameter comes from the entire population. So a statistic is called an unbiased estimator for a parameter if the mean of the sampling distribution for that statistic is equal to that parameter. Okay, that's a bit abstract. Let me give you examples that will help. So the biggest, most important example is the sample mean. The sample mean is an unbiased estimator for the population mean. We're assuming, by the way, that you are you don't have some kind of like bias sample. You know, given that you have a good sample, like a random sample, then the sample mean is an unbiased estimator for the population mean. What that means is that if you take a sample without bias, okay, so you use some random sampling technique or really good stratified sampling, and you look at your data, you find the average or the mean of your data, then that is the best guess for the population mean. Okay, you won't know exactly the population mean, okay, but you could say that's your best guess. Does that make sense? And there's a lot of things you'll never know the population mean of. For example, if I wanted to find out the population mean weight of all people on Earth, how heavy they are, can I do that? Can I find the population mean weight of humans on Earth? What do you think? Yeah, the answer is absolutely not. That would be impossible, right? There are billions and billions and billions of people on Earth, and you can't weigh them all. Can't even find like half of them. Good luck. But you can't get all the weights of all people on Earth. It's not possible. Okay, but what I can do is maybe, if I have a little bit of money, I can go around. Probably I have to go from country to country because I wouldn't just go to America. That would be biased. And I would go to a bunch of countries, kind of get a nice, random, maybe stratified sample and weigh maybe 5,000 people that are a representative sample and take the sample mean for those 5,000 people. That would not be the same as the population mean for all people on Earth, but it would be a best guess for it. Any questions on that idea? And that's saying that the sample mean is an unbiased estimator for the population mean. Is that clear? Okay, and maybe I don't have time to do 5,000. Maybe I can only do, let's say, 25 people on Earth. But as long as I do a random sample, that's an unbiased estimator. And that's the best guess. Not perfect, but it's a better guess than not doing anything. Okay. On the other hand, the sample range is a biased estimator for the population range. So if I grab 30 random people and weighed them and took the range of those 30 people, is that a good guess for the range of the weight of people on Earth? Yeah, it's a terrible guess because the range is the heaviest minus the lightest, right? The lightest person on Earth probably was just born, like within a day or two, right? It was probably some really tiny baby. Who knows what country they're in? Nowhere near probably some, of 30 random people I can find. It's probably gonna be nowhere near the lightest person on Earth. Okay, that little tiny infant that was just born and born tiny, way premature. Do you see? And also, the range is the heaviest minus the lightest. Well, the heaviest person on Earth, that is one big fat person. Hundreds and hundreds of pounds. Okay, if I randomly select 30 people, I'm almost certainly not going to get someone that is 300 pounds. Okay, I have no idea how heavy the heaviest person on Earth is, but they're a lot heavier than just some random 30 people and pick the heaviest there, usually. So the sample range is a terrible estimator for the population range. Any questions on that? Okay, it turns out the sample proportion is also an unbiased estimator for the population proportion. Okay, so the two main ones in our class that we're going to be using are the sample mean and the sample proportion as using the sample to get the best estimate for the population. Any questions on that? Any questions on the idea? All right, now comes the big theorem. This is huge. So I'm going to go pretty slow on this because we're going to be talking about it and using it pretty much every week for the rest of this class. And this is called the central limit theorem. And it has two parts. And by the way, it turns out you can do the central limit theorem for means, the central limit theorem for proportions, and the central limit theorem for sums. I'll go over all three of them. They're slightly different, but they are the same idea. What it says, for the means at least, is the sampling distribution. Let me make this a little bigger. The sampling distribution for sample means from samples of size n. So that's what we were talking about is you can do a study, maybe looking at ages of baseball players. And if you looked at all different samples of, let's say, size 3 of 3 different baseball players, and you looked at their averages, and you're going to get a whole bunch of different groups of 3, and each one is going to have a different average. But if you take the average of all the possible sample means, so the population mean of all the possible sample means, then that will always equal the population mean. Okay. This part A is the same thing as saying that the sample mean is an unbiased estimator for the population mean. That's what unbiased estimator means. So the mean is the same. Any questions on that? Okay, the standard deviation, sigma sub x bar, if you look at all possible sample means, that is not going to be the same as the population standard deviation. It is equal to sigma over the square root of n. So the population standard deviation divided by the square root of the sample size. And that's very important. If you had, say, a sample size of 100, then you're going to reduce the standard error by a factor of 10, because the square root of 100 is 10. And remember that this sigma sub x bar gives you kind of an idea of how far your sample mean will likely be from the population mean. And if you're doing a survey to try and get a good estimate for the population mean, you want your sample mean to not be far from the population mean. You'd love it to be exactly the same, but it's almost never exactly the same. But if you want it to not be very far from the population mean, then what you do is you make n very large. You have a very large sample size. Okay, so if you do a sample size of 100, you have dropped that spread, how far it's likely to be from the population mean, by a factor of 10, which is a nice thing to do. Any questions on that idea? I don't expect you to fully understand it, but we'll have a good example, one important one, and hopefully it'll be important in your lives also. Definitely in mine. But then we have part 2. Part 2 actually has 2 different types. If the population's distribution is normal, which is usually not the case, by the way. Usually the population distribution is not normal. Okay. And by the way, when you did your projects and you looked at the histogram, most of you probably looked at histogram and it didn't really look that normal. It might have been skewed right. Skewed right is most common for the projects, by the way. Doesn't mean they all are. But most population distributions aren't normal. But if you happen to have one that's normal, then you can not worry about the next statement, but usually you have to. Or, here comes the next statement. If the sample size is large, in our class, large will mean greater than 30. That usually gives you one significant digit of accuracy, okay, at least. So over 30 is the standard for how big a sample size you need to be able to state what we're about to say. And that is, then the sampling distribution for the mean is also approximately normal. And that is huge. So that means that if you are conducting a survey, unbiased, you always have, if you have bias, you can't do anything, by the way. You're conducting an unbiased survey and you look at your sample, then you can say, look at the probability that the sample mean that you would get would be bigger than a certain distance from the population mean. Well, to find probabilities, if you don't know the distribution, you can't find the probability. But guess what? If you have a sample size over 30 and you have an unbiased sample, then you have a normal distribution and you can do calculations. So that this is true basically for any unbiased survey. Isn't that great? As long as you have a sample size bigger than 30. If your sample size is not bigger than 30, let's say it was 15, and you know nothing about the distribution to start with, then you can't use normal distribution. And basically, you can't do anything we do in our class from now on, because without knowing what the distribution is, you can't do a calculation of anything, because you don't even know where to go. If it's normal, that's different than if it's uniform, which is different than if it's skewed left. So you wouldn't know how to do anything. But if it's normal, then you can use a calculator. Any questions on this big, big theorem? So look at it, make sure you get it, because it is the most important theorem of the entire course by far. On a scale of 1 to 10 of importance, any guess on what this was ranked for statistics? Yeah, 10. 10. Okay, not a 9.9, by the way. It's a 10. Okay, it is the most important by far. So get this down. Any questions? All right, so now I want to do some examples. And I want to do one that's really important, I think. It's helped me a lot. And when I say helped me a lot, I've made a lot of money. Okay. By the way, including this week, over $10,000 I made, because I understand this stuff. So, by the way, next week I might lose a bunch, but this week I made a lot. Okay. Let's suppose you put $10,000 into the bank. Okay. Sounds good? Okay. What is the probability that you're going to end up losing money after 1 year? So what is the probability that X is less than 0, where X is the amount of money that you, or maybe the percent gain that you have. And if the percent gain is negative, that means you lost money. And I actually went online last night and I asked the computer, what is the average interest rate for banks in America? Not Bank of America, but banks, just American banks. And it told me 0.46%. What's the probability that if you put $10,000 into the bank, okay, one of the big banks, you know, Wells Fargo, Bank of America, whatever, US Bank, one of those banks, what's the probability that a year from then, you're just going to let it sit in the bank, you're going to end up losing money? What do you think that probability is? The hint is it's really easy. Put in the chat box. What is that probability? You don't need a calculator. That's a hint. You want to round it 10 decimal places, that's fine. Because it's easy. That's how easy it is. I don't see y'all jumping in. All right, maybe I'll tell you because I don't see an answer. It's 0. You put money in a bank, a year later, you can take it out. Okay, and you're going to make 0.46%. Right? And 0.46% of 10,000, by the way, is what, $46? So is that a good investment? What do you think? What's your thought? Is it a good investment? The answer is, it depends. What's good about it is it's safe. Okay, if you don't know about what this means, FDIC insured, even if the bank goes bankrupt, then the government will still give you your money. I don't know if you know that, but that's how our United States law is. So still get your money back. That's why there's a 0 probability of losing. So even if the bank falls apart, you still get your money back. So that's good. But are you going to make a whole lot of money? No. You're making $46 out of 10,000. 0.46%, given there's inflation, your value's gone terrible. Any questions on that? What's another option if you have $10,000 besides putting it in the bank and you don't need it for another year? Any thoughts? Okay, we can invest it in a CD. CD is like a bank, though. You get a little higher percent, but it's the same idea. But you can invest it, how about in a stock? The stock market. So now let's do a different one. So suppose you put 10,000 into a randomly selected stock. Okay. The mean rate of increase of stocks is about 9%. So 9, but the standard deviation is about 20%. Okay. Let's assume the stock returns are normally distributed. What is the probability you're going to end up losing money now? This is a little bit harder to figure out, but we can. And the key word is right here. Normally. That means we have a normal distribution. So that means we can use the calculator and we can use the normal distribution calculator. The low will be equal to, if you want negative, losing money means as much down as it goes. Okay, maybe you could write negative 100, but I'm going to use negative a bunch of 9s. The high will be equal to 0 because anything less than 0, you lost money. We know the mean and standard deviation is 9 and 20. So let's find out. Go into our calculator. And I go to the normal probability calculator. The low was negative a bunch of 9s. The high was 0. The mean was 9. And the standard deviation was 20. Anyone, any questions on that? Because we're assuming we have a normal distribution. And I calculate it. And now we have about 0.33. I'll round it to 2 decimal places. Okay, if you're really going to need that money next year, do you think this is a good investment? What do you think? Let's say this $10,000 is going to be used basically for your tuition for next year in college. And if you lose it, you're going to have to drop out of college. Do you think it's a good investment? Any thoughts? Should be obvious. Not a trick question. Yeah, if you have a 33% chance that because of this investment, you're going to drop out of college, I hope you think college is more important than that. Then this is a terrible investment. Okay, even though it has a return of 9% on average, 9% of 10,000, by the way, is $900. That's a lot better than the bank in terms of what you're getting back, but it's risky. You might lose money. Any questions on this example here? Okay, so let me give you another investment possibility. I'd like to, my hope is that you'll realize by the end of this course that you're going to learn all kinds of things that will help you in life. Okay? Besides just being able to read an article, but actually investing money, for example. So now let's suppose that you put your $10,000 into a Dow Jones index fund that has 30 stocks. Okay. Okay. And what's the probability now of losing money? So we're going to assume the Dow Jones is a representative sample, unbiased, and that let's suppose stocks are independent of each other, which isn't quite true. There's more to it than that, but I can only do so much. And 30 is not quite enough for normal distribution. So we're going to assume it's like not that far off from being normal. And then you're okay. Still going to have mu as 9 and sigma as 20. That doesn't change, stocks. But we now have one more important number, and that is n. N equals 30. And now we can use essential limit theorem. The essential limit theorem says that X bar has a normal distribution approximately. Okay, 30 is not that far from, it's not over 30, so it's not perfect, but we're going to assume that we started normal, so we're good. The mean of all possible sampling distributions will be the same as the population mean, which was 9. The standard deviation will no longer be 20. It's going to be sigma over root n, or 20 over the square root of 30. So let me stop because this is the important thing for today. Any questions on how I came up with the distribution for the sampling distribution for this example? Okay, whenever I ask you for a sampling distribution, you better have that little tilde there. It's on every keyboard, so I don't feel guilty. Okay, just let you know that if it says what is a sampling distribution, and you got to type it out, just remember the tilde, and that'll get you going to the next step. In this case, it'll be n. You know, a couple weeks ago we had a U for uniform. Okay, and then if it's normal, mean, standard deviation for the essential limit theorem, it'll be sigma over root n. I put that 20 over root 30 in my calculator, and I got about 3.651483.717. Any questions on that? Okay, so now we need to find out what's the probability of losing money. Well, the low and the high will be the same as what we just did. You know, losing money means that you lost an unlimited amount, basically. And 0 is that borderline of losing money. Anything higher than 0 is winning money, or making money. But now the standard deviation is going to be this big number here. So if I go back to my calculator, same low, same high, same mean, standard deviation now will be that 3.6514, etc. Leave the P blank and hit calculate. And what do we notice? What do you see? You look at it, it's a very small chance of losing money, 0.007 or so, rounded to 3 decimal places. So what do you think? Is this a good investment? Yeah, you get a much higher interest rate than the bank, and your probability of losing money is almost nothing. Okay. I do want to give you a heads up, though, in case you do invest, and that is we did some assumptions, and that is that Dow Jones is representative and that stocks are independent of each other. That's not quite true. If you invest long term, longer than 1 year, like 30 years, you're pretty good about it. Okay. If you want them to be independent of each other, what should you do? Anyone know the kind of vocabulary that you hear in economics? It's a word that you've all heard before, but I'm not sure if you can think of it. To make sure they're independent of each other. Anyone know? Okay. So in the stock market, we talk about, or in investing, we talk about a diversified investment. I'm sure you've heard that word, right? And that's what a diversified investment is, or diversified portfolio, sometimes you'll hear. And that means that you have more independence of each other. Whereas if all the stocks that you buy are in kind of a similar industry, then that's independent of each other is a very bad assumption. So if you want to have a safer investment, then you want to have a diversified investment so that you can use essential limit theorem. Any questions on this? Okay. By the way, do you think I've used this to make money? Think I use statistics to make money in the market? Absolutely. I told you, I made like over $10,000 this week. Okay. By the way, some weeks I lose a lot too, but this week was a very good week. Or I say this week, I'd say the last four days or so, maybe 3 or 4 days of the stock market. I shouldn't say this week because it's only Monday. But if you look at the last 4 days of stock market, it's been very good for me. I made a lot more in the market than I did in teaching this month, by the way. Just let you know. And that's because I use statistics and it works. Okay, it's a good thing. And hopefully you'll learn some stuff too. All right, let's give you a different thing. Let's suppose you want your standard error to be equal to 2. Okay. How big a sample size do you need? And note that our standard deviation is 20. So if you want the standard error to be 2, that means we need to reduce that standard deviation pretty much. And the formula says, well, the essential limit theorem, so it's a standard error, is the standard deviation over the square root of n. So 20 over root n. Okay. And we want that to be equal to 2. 2, by the way, is 2 over 1. Okay. We can cross multiply. 20 times 1 is 20, equals 2 times root n. Divide by 2, and you get 10, equals root n. Square both sides, n is 100. Okay, so if you wanted the standard error to be 2, then you would have to diversify with 100 different independent stocks. Any questions on that example? A little bit of math in this one. Some people don't like math, but this is a math class. We are in the math department, so there's a little bit of math. Any questions at all on this example. Okay, so a lot of times you might even look at some study that you read on and say, why did they have to survey 1,000 people? And it has to do with this calculation. They decide what their standard error should be. They do the calculation, and then they find out what their sample size is. And then they go and do the sample. Any questions at all? Okay, let's go to the next big theorem. And this is the central limit theorem for proportions. And it says the following. Okay, P is the population proportion. Okay, we don't use the Greek letter, by the way. Do you know why? Because for population, we'd be using Greek letters for everything, right? Anyone know why we don't use a Greek letter? The hint is you have to look at my shirt. I wore this on purpose. What's the Greek letter for P? You all know it. Yeah, it's pi. And that confuses the hell out of everybody. Because when I first taught, that's what everyone used. They used pi, and boy, students had so much trouble because they wrote 3.14. It wasn't right. So we don't use pi anymore. We use p for the population proportion. And we put a little hat on top of p for the sample proportion. We call that p hat. You're welcome to write p-h-a-t, just like I do. If you don't want to figure out how to put a hat on top. Hats are hard, by the way. Not easy to figure out how to put that hat on top on it, if you're typing, by the way. If you're writing, it's easy. But if you're typing, it's hard. Okay. And just to note, Q is 1 minus P. Okay, so P is a proportion of people, or proportion that says yes to the survey question. What is Q? If Q is 1 minus P, what is Q? Kind of in idea or words. Thoughts? Not that tricky, by the way. Don't see you jumping in. Okay. Q is 1 minus P, which is a proportion that say no. If 80% say yes, 20% say no, which is 100% minus 80%. Any questions on that idea? Okay, the sampling distribution for sample proportions. Because remember, I mentioned that the sample proportion is an unbiased estimator. So it's a good thing for, using statistics and for doing it, getting your best guess of the population. And the sampling distribution says mu sub p hat equals p. So if you look at all possible sample proportions with the same sample size and you average them, you end up with the population proportion because it's unbiased. Okay, the next one's a little complicated. The sigma sum p hat, or the standard error for the proportions, is equal to the square root of p times q over n. So important formula. I don't make you memorize any formula, but I would keep it near you when you're doing your work in the next few weeks because it's useful. So it's a square root of pq over n. Something to note, if you look at the denominator, it's n, and there's a square root. So we still have over the square root of n, just like we had with the central limit theorem for means. So if you want to reduce your standard error, it's the same idea. Make the sample size bigger. And your reduction will be the same type of reduction as we did for means. Any questions on that? Okay, now comes a piece that a lot of people have trouble with. If NP, the predicted number of yes answers, and NQ, which is the predicted number of no answers, are both larger than 5, then the sampling distribution is approximately normal. So if you have your predicted number of yeses and nos, that's NP and NQ, and those are both at bigger than 5, at least 6, then we have normality. And that means we can use the normal calculator. Okay. Just the big mistake people make is they don't pay attention. If this is a survey question, that's a yes/no survey question. Do not see if your sample size is bigger than 30. That would be wrong. What you do is you say, what is NP? What is NQ? Are they both bigger than 5? In our class, we're going to use 5. Some other textbooks you might see will use 10. Most use 5. So I use what most people use. All right, so here's something I want you to do. I want you to put in the chat box if you are here live. If you're watching this as a YouTube video, I want you to write it on paper and write, for a yes/no answer, I will not use the number 30 to see if the sample size is large enough. I want you to put that in the chat box right now. I want you to there's a promise, by the way. You're putting it in because you're promising you won't do this. So if the survey question has a yes/no answer, I will not use the number 30 to see if the sample size is large enough. I want you to put it in the chat box. Type it in. It's worth spending the time. And there's a reason I'm telling you this. And again, watch it. If you're watching this on YouTube, then write it down on paper. Make the promise. And I'll give you a minute. I'm watching the chat box. Still watching. Good, good. Okay, so you've all got it in. So do not break your promise. Got it? If you break your promise, I'm going to take off a lot of points. Just a warning. So do not break your promise. You've made the promise. Okay. The reason I make you do this is you don't know how many people make this mistake. So I want to force you not to make the mistake. All right. So now let's do an application. And one of the things like I said, I love about this class is that I can find applications to anything. And for this one, I went online and looked on the news, and I found, and especially since I told you today is the day that I put AI into this class where you can actually use AI to ask questions about the textbook. Okay. So what I did is I looked up and I found an article, somewhat recent article, and it said fewer than half of all college students have used ChatGPT or a similar AI application like MathGPT. Okay, that's what it said. So the question is, do we believe the article? Do they know for sure that this is true? That fewer than half of all college students have used ChatGPT or a similar AI application? Yeah, they don't know for sure. Did they ask you? Did they survey you? I've never had anyone say yes to did they survey you question. One of these days I might get one, but never happens. They don't know everyone. They don't know the population. So why did they say it? Why are they saying that fewer than half of all college students, not just their survey, but all college students? So here's what it is. By the way, this was a best colleges survey. That was the name of the company or whatever it was. Their sample size was 1,000. I looked it up. And it said that of the survey of 1,000 Americans, 43% have used ChatGPT or a similar AI application. Okay. By the way, 43%, hopefully you know, is fewer than half. Does that mean fewer than half of all college students in America have used ChatGPT? Doesn't mean that. So that, you can't exactly say that. On the other hand, what they are more interested in is being right most of the time. Okay? If they're right 99% of the time, they can say this and it's okay. Does that make sense? If they're only right, say 60% of the time, then they're going to lose credibility as a news company, right? Or a survey designer, whatever this group is. So that's what happens, is we want to find out the following. Okay. And by the way, I do have a link here, but I'm not going to go to it. We want to find out what is the probability. Let me write this down. What is the probability that if half, so 50%, the 50%, then they're wrong about fewer than half. That's like the smallest percent and them still being wrong, right? That if 50% of all college students have used AI, such as ChatGPT, all right, or MathGPT, since that's what we talked about earlier. Then if they surveyed 1,000 randomly selected college students, that at most 43%, because that's what they got, have used AI. Any questions on the question? Any questions? Okay, I have it up here too, but I wanted to do it again. It's so important. That's like the whole point of what we're doing, is to be able to answer these kind of questions. So then we say NP, N is 1,000, that was the sample size. P is our assumed probability, which was 50%, 0.5. If I take 1,000 times 0.5, I don't need a calculator, that's 500. Half of 1,000 is 500. And I hope you all know that 500 is a lot bigger than 5. NQ is 1,000 times 1 minus 0.5, which is also a lot bigger than 5. Any questions on that? So because of that, we can say by the central limit theorem for proportions that the sampling distribution is normal. So we could say p hat, so that means all possible sample proportions. Tilde means it has a distribution that is n normal. And again, if we go back to the Central limit theorem, mu sub p hat is p. Our p was 0.5. Sigma sub p hat is root pq over n. So that's going to be 0.5, comma, the square root of 0.5 times 1 minus 0.5, which happens to be 0.5, over 1,000. And I worked that in my calculator, and that square root became 0.0158. Any questions? Any questions on applying this? All right, so now we want the probability that we end up with at most 43%. What's the low? What's the low if we want the probability of at most 43%? What is the low? And there's two answers. I'll take either of them. They'll both work. Yeah, okay, so you can go 0. You can either go 0 or negative 99999. Either way works. You'll get the same answer, it turns out. What's the high? 43, actually 0.43. Don't forget to turn into a decimal. Is that clear? So the high is 0.43. What's the mean? Yeah, 0.5. And the standard deviation is this 0.0158. So I can go into the calculator. The low was negative bunch of 9s. The high now was 0.43. The mean was 0.5. The standard deviation, let me look again, was 0.0158. And there's our probability. And you look at that, it's 0.0000047. It's extremely low. With that low a probability, if you, let's say, were the manager of this company, would you feel comfortable saying that 50% assumption is wrong, fewer than 50% have used AI? What's your thought? Okay, you should feel fine. If you have this probability of having a news article that doesn't quite tell the truth, you should be okay. If news is right 99.999% of the time, you got an amazing news station. Does that make sense? You should be fine as a manager saying that's good. Do you see? Because you can be real comfortable that 50% assumption must have been wrong. Because if it was right, then you would have this tiny, tiny, tiny probability of getting 43% or less. Any questions on that? And that is really what this course is all about, by the way, to be able to answer those kind of questions and use them. Okay, it's very important. We're going to be doing that in 2 weeks especially. And we're also going to be using it next week for a different application, which we'll get to. Not today. Any questions on that? All right, so now the last central limit theorem, and that is the central limit theorem for sums. This comes up here and there. Sometimes you care more about the total instead of the average, or the sum instead of the average. Really, it just depends on the situation. When do you think you might be more interested in kind of stating the total instead of stating the average? Can you think of an example? Thoughts? If you can't, then I'll give you one. There are a lot of examples. All right, so if you don't know example, let me give you one, and then we'll do another one too. Let's suppose you worked in a restaurant. Okay. And you're in wait staff. Okay. And by the way, how do you get paid if you're a waiter or waitress? If you're on wait staff? Where's your big money coming from? Yeah, tips. Tips. So if that's your job, and do you think you care if you're thinking about, getting a new job at a restaurant, do you think you care more about the total or the average tip? The total for the day or the average? The total. Okay. What matters is how much at the end of the day you come out with. Okay. You know the average, but you don't have many. If you have a high average, but not very many customers, that doesn't help. Do you see? So that would be an example where total is most important. There are many others. So here's another. So here is another restaurant example. Now let's suppose you, instead of wait staff, now let's say you actually own the restaurant. And let's suppose that the average customer at a restaurant spends $33.23. Okay. Okay. Which, the funny thing, I think when I originally wrote that was like a pretty high price restaurant. Not anymore. Things have changed. Okay. And the standard deviation is $9.22. And by the way, you do that by collecting some data and seeing what happens, right? Okay. If 65 customers eat at the restaurant today, okay, what's the probability that the total revenue for the restaurant will be less than 2,000? And what is the first quartile for the total revenue for a day? Any questions on the question? Okay, very important, by the way. Okay, so let's start out with the first question. And even for both of them, you're going to need to do the same thing. What we're going to do is we're going to use the central limit theorem. Total is this, by the way, this symbol right here, that is a capital sigma, and that means summation, if you haven't seen it before. So it's mu sub, add all the x's together. And that equals n times mu. And sigma sub, add all the x's together, equals sigma times the square root of n, not divided by. Okay, pay attention. Pay attention to the question you're asked when you're doing your assignments or you're doing your exam, because you get it wrong and you do average instead of total, it's just wrong. So make sure you really pay attention to what the question is asking for. Okay, and by the way, same as central limit theorem for means, if the population's distribution is normal, or if the sample size is larger than 30, then the sampling distribution for sums is also normal. Any questions on that? Okay. We can also say the total, that's that capital sigma, tilde, so has a distribution that is n for normal, whose mean now is n mu. So notice the mean is bigger. which makes sense. If the average customer spends, $33.20, and you have 65 customers, you don't expect to total $65. You expect to total 65 times, 65 times 33.23. You don't expect to total 33.23. You expect to total 33.23 times 65. So that should be obvious. The sigma times root n, basically, to fully understand why that's true, you probably need to be a math major. And my guess is none of you are math majors. And if you're not, if you are, tell me, but I doubt it. There's a lot of calculus in this stuff that we just hide. Okay. So because of that, our total tilde n has a normal distribution of the sample size, 65, times the mean, the sample mean, the population mean, which is 33.23. And the standard deviation is the population standard deviation, which is $9.22, times the square root of 65, squared n. Any questions on that? I worked out in my calculator, and I got $2,145 for the total, the expected total, okay, or the population mean of all totals, and 74.334, which was 9.22 times root 65 for the standard error for totals. Any questions on that? All right, so then we can now put everything in. So if we want the probability that the total revenue will be less than $2,000, what's the low? What's the low? Not 2,000, not 2,000. The low would be 2,000 if you want the probability that it was greater than 2,000, not less than 2,000. The low if you want a probability that's less than 2,000. Yeah, negative bunch of nines. Okay. And this is one of those you need a bunch of nines because 2,000 already has 4 decimals, so at least 6 nines. Okay, and the high? What's the high? Yeah, 2,000. So then we just put it in. Our low is negative 99999. Our high is 2,000. Our mean was 2,145. And our standard deviation was 74.334. We want the probability, so we leave that blank. We calculate. And that is about 2.0255. So the answer is there is a 0.0255 probability that the total revenue will be less than $2,000. very important in kind of understanding business planning and stuff like that. That gives you an idea of, on a bad day, you're still probably going to make, close to $2,000. Not a problem. Does that make sense? Okay. Yeah, we have all kinds of assumptions about, unbiased sample and stuff like that. And not a bad day, bad day that has 65 customers. So if you have 65 customers, then you're still going to make, a revenue of probably at least 2,000 because you have a very small chance of getting less than that. All right, then what is the first quartile for the total revenue per day? When we say first quartile, what does that tell us? What does it tell you if it's the first quartile? We saw this before. This isn't new. Yeah, it means that 0.25, but in particular, the probability is 0.25 or P equals 0.25. So P for this next one will be equal to 0.25. And we want the first quartile. So we go to the calculator. And still the low is a bunch of negatives. Negative 9. The high is what we want. Mean and standard deviation don't change. And our probability is 0.25. Any questions on that? And hit calculate. And there it is. I'm going to go 2 decimals because that's like to the nearest penny. Maybe nearest dollar would be enough for a manager, but let's go to penny. So 2,094.86 will be the first quartile. So that means that 25% of the time, if there's 65 customers, you're going to get a revenue of less than $2,094.86. And 75% of the time, you get a revenue of more than $2,094.86. Any questions? Any questions on this example of the central limit theorem for sums? It's very easy to come up with examples that actually are useful for all kinds of businesses, okay, or all kinds of strategies, or all kinds of understanding of society, or whatever it might be. This is used all over the place, okay, and we're going to be doing very specific. Next week, we'll do confidence intervals, and we're going to be using the central limit theorem. The week after, we're going to do hypothesis testing. And actually, all the weeks after, we'll do hypothesis testing. And that will also use the central limit theorem. Without the central limit theorem, basically, we wouldn't have statistics. It would just kind of not be taught because no one would use it. That's how important this theorem is. So any questions at all? All right, the next thing I'm going to give you is a secret word. Okay, and I guess maybe I should put in quotes because it's not really a word. It's a secret form, it's an equal expression, NP. So the secret word is NP, because if you happen to have a yes/no survey question, then you want to see if NP is greater than 5, and NQ also has to be greater than 5. And then you can use the central limit theorem and say that you have a normal distribution. By the way, if either NP or NQ are not bigger than 5, you can't do anything. You shouldn't even do statistics. Okay, you just need a bigger sample size. So that's a big note, is that if you don't have NP and NQ both bigger than 5, you screwed up. It means that you have worthless data. So NP is our secret word. So hopefully you at least have a good idea now The central limit theorem for means, the central limit theorem for proportions, and the central limit theorem for sums. I do want to give you a heads up. Don't use this in project 1. Project 1 doesn't go over that. It doesn't do anything with that. Okay, that'll happen in project 2, but not project 1. Okay, so you do have project 1 due on Sunday, and hopefully you have made lots of progress. What I'm going to do is I'm going to stop the recording, but I'm going to answer questions. That could be about central limit theorem, but it also could be about the project. So let me hit stop the recording.